All right, so this is Math 331, problem solving, and in honor of opening day today, I want to give a baseball lecture. So this was inspired by a question that I was asked many years ago when I was teaching mathematical statistics at Brown. How many of you have heard of the Pythagorean one-loss formula? Okay, so at least most of you have not heard of this, so it'll be a new thing. Now, how many of you do not care about baseball? It is okay to say you don't care about baseball. All right, so good. So then since nobody is saying that they don't care about baseball, then I've already sufficiently motivated the topic because we'll see about how math applies to baseball. So why am I doing this in problem solving? The real reason is I want to talk to you about how do you approach a problem and use mathematical tools in a new setting. That's the main motivation for today. When you have a problem where you already know, you're doing Calc 1, Section 3 is on the chain rule, gee, I wonder what I should try to solve the problems here. Or in our class when we're doing proofs by induction, I wonder what I should try to do for those problems. How do you handle something new? How do you handle something where it's not immediately clear what you should do? And how do you judge success? So what I'm going to do is I'm going to split up the final into different parts. You won't have to do all the final at once, and this way if the final is not going well, I will have a chance to give you feedback before the semester is over and there's no chance to make a course correction. I am not allowed to mention the organization while the camera is rolling. Is this still in focus? Okay, so I was part of an organization. I was at the national meeting a few years ago, and the way it works is for every position, you must have 2 candidates. And you must receive over 50% of the vote to be elected. So we had to elect 9 people from 18. On the first ballot, you can vote for as many people as there are open spots. We elected maybe 3 or 4 people. By around the 3rd or 4th ballot, we were having trouble, and we reached the point where we only had 10 candidates left, and we had to elect 1 out of 10. And that person had to receive over 50% of the vote. Now with 10 candidates, it's extremely hard to get over 50% of the vote. And so we had already failed once or twice, and so somebody raises their hand and suggests that we change our voting procedure and we just vote among the top 2 candidates. This requires a 2/3 or a 3/5 supermajority because we are changing the voting procedure in the midst of an election. That motion fails. It gets close to what is needed, but not quite the critical threshold. Then somebody else makes a motion that we should just not vote for whoever had the fewest votes, which is, of course, changing our voting procedure, which requires another supermajority, which fails. I then raise my hand and say, Steve Miller, Williams College mathematician. I'm not making any motions, but if people want to just not vote for whomever received the fewest votes, thank you. It took, I think, another 2 more ballots because somebody made a motion to adjourn. And so motions to adjourn always take priority over anything else. But eventually, after 6 ballots, we were able to get all the candidates elected. Several people have commented to the national organization about their memories of that meeting, including the fact that it took 6 ballots to elect people. And they want something better. So unfortunately or fortunately, I spoke up at the meeting and offered to come up with a better solution. So part of your final exam and part of a project that we're going to do is actually look at how can we do a better voting system. This does not mean that we are looking for the best voting system. What kind of system do you think we're looking for? So this is problem solving. This is a new problem right now. I'm throwing it on you. What is my metric? What do I want to use to judge whether or not I've done a good job? Everyone is happy. Now, you're not going to get everybody happy. I'm in Williamstown, Calvin right now, and there's a lot of parents who are not happy, and there are some parents who are happy. You're always going to piss off some people. So given that you're going to piss off some people, what do you think you want to try to do? Yes?
Maybe minimize the number of ballots necessary.
So one thing is maybe minimize the number of ballots so that we're not going through 6 ballots. Maybe we do it in at most 3, maybe 4. So one thing would be trying to get a method that will guarantee we finish earlier. One is also trying to minimize how many people are pissed. Another is trying to have everybody feel that the method is fair. Do you think we want the most complicated thing or the thing that's easiest to explain? Probably, yeah. And so there's going to be a trade-off. And we're going to see that in what's happening today. Is the most accurate formula. You then have to explain to people why you're using that. And sometimes it's easier to use a simpler formula that does a pretty good job, and people can see that that looks reasonable. And it's an extremely fascinating trade-off, because at the end of the day, you have to explain things to people. And if things get too complicated, interesting things can happen. At the same meeting, we were making a motion to condemn gun violence on college campuses. And the resolution started getting more and more complicated as people were putting in various things. And on I think, fourth phrasing, they finally typed it up and put it on the screen. And at about 8 or 9 seconds after they displayed it, half of us burst out laughing and raised our hands because a comma was in the wrong place. And the motion was now advocating arming everybody on campus, which we were pretty sure was not the intent. But when things get very complicated, there's a chance of making an error. So the simpler thing you can do, the better. All right. So let's hope this works. OK. So this is dedicated to my great uncle Newt Bromberg, a lifelong Red Sox fan who assured me when I was a little kid. Is it a little bit off?
Yeah.
OK. Who assured me when I was young that I would live long enough to see the Red Sox win the World Series. When the Red Sox won in 2013 and I woke up camp to see the end of the game, he remarked, "I did it younger than you did, Daddy." OK. So this is Wally, the new mascot for the Red Sox. Anybody know why he's number 97? Year he was introduced. So the Pythagorean one-loss theorem, when you hear Pythagoras, you should be thinking about all the stuff we've been doing on triangles that has absolutely nothing to do with what's going on. Baseball is played on a diamond unless you draw the line from home to second or look at the triangle in the outfield in Fenway Park. It's not about triangles at all. So an interesting question is, why is it called the Pythagorean one-loss theorem? And so I'll let you ponder that a little bit as we go through it. So the goals of the talk is I want to give a derivation of the formula. I want to talk to you about ideas and techniques of mathematical modeling. And it's how do you take a complicated system and distill the key features? Because if you're going to be a problem solver, if you put too much stuff on the plate, you're not going to be able to get anything tractable. So you have to decide what are the key features. Have we talked about Galileo's experiment, where he dropped 2 spheres to see if the mass affects how long it takes to fall? How many of you have heard of this experiment? Okay. What were the color of the spheres? Right. That's not really survived from the experiment, because the color does not really matter. Unless perhaps one is black, one is white, they've been sitting outside in the sun for a long time, one is now really hot, one is cold, and that maybe the heat has something to do with how they fall through the atmosphere. But as long as you're not in a situation like that, the color's not going to matter for an experiment like this. That's not a feature we need to include in our model. It is extremely challenging to keep track of what things really matter. I want to show you how advanced theory enters into really simple problems. Part of this is the hammer technique. If all you have is a hammer, pretty soon every problem looks like a nail. If you know something, can you find a way to bring it in? Also, there's a reason the problem is not solved. People have already tried various things. And if they could have solved it using those techniques, they would have. Or maybe they just haven't even thought of asking these questions. The last is opportunities from inefficiency. How many of you have seen the movie Moneyball? Okay, Moneyball is a great movie about applications of mathematics. And you have these wonderful situations where people value certain quantities incorrectly. And if they value things incorrectly, you have an opportunity to take advantage of it. Or if you want to teach them a lesson, a very expensive lesson. So one of my favorite statistics in baseball is the save statistic. So the way a baseball game works is whoever scores the most runs wins. How many of you know what a save is in baseball? Okay, for those of you who don't, does a save sound like something good? Yes. It sounds much better than an F-up, right? Or something like that. This is being recorded, so I'm going to be a little bit careful with my language. I wish they actually had a statistic like that to record how often somebody just completely collapsed. But so, a save, you think, oh my God, we were teetering on the brink of disaster, and they saved us. So the way you typically get a save is if you record the last out, and when you come in, your team is winning by 3 runs or less. There is another way to get a save. If your team is up by any amount of runs, and you pitch the final 3 innings, you get a save. So the Baltimore Orioles turned out to be a really good team for interesting examples. A couple of years ago, they were playing the Texas Rangers in Texas. And after 6 innings, the Texas Rangers were beating the Baltimore Orioles 14-3. So they're up by 11. There's 3 outs in an inning. Baseball has 9 innings to go. The Rangers needed 9 outs. They could have alternated home run out, home run out, home run out, and they still would have won the game. They had that big of a lead. You know, average baseball game scores between maybe 4 and 5 runs. The Rangers brought in a relief pitcher who pitched the final 3 innings without giving up a run. Meanwhile, in their 2 at-bats, the Texas Rangers scored an additional 16 runs. The final score was Texas 30, Baltimore 3. And he gets a save because he pitched the final 3 innings, coming in with an 11-run lead and getting an additional 16 runs of support. I don't know about you, but when I hear save, this is not a situation that strikes me as a save. So what a great baseball manager, Billy Beane, did is he inflated certain pitchers' perceptions by having them become master savers. It's like, oh, geez, you want my great relief pitcher with all those saves? Oh, I hate to trade him, but I need a second baseman. Okay. No, you can only do this so many times before people start to catch on, but you can do it a few times. And so because people were overvaluing saves and undervaluing something called on-base percentage, he was able to make a killing on many trades. And so that's one of the big things that you want to be thinking about is, what is the right metric? What is the right thing to value? And if somebody values something differently, you have an interesting opportunity. Okay, so the goal is to find statistics that describe the real world. So this is one of my favorite statistics. This is the Harvard Bridge, about 620.1 meters. Anybody know why I'm showing this? What are the 2 great schools in Cambridge? And MIT. So this involves MIT and a fraternity. In Smoots. Yeah. So Smoot was an undergraduate at MIT, and a fraternity decided it would be interesting to see how many Smoots the bridge is from end to end. So they would pick him up, mark, pick him up, mark, pick him up, mark. The Cambridge Police Department didn't really find this amusing, and they got the marks erased. Well, this just can't stand. So they take Smoot again, and this goes on, and eventually it gets to the point where everybody loves the Smoot marks, and if there's an accident on the bridge, they now report how many Smoots from the end of the bridge the accident happened. So the bridge is 364.1 Smoot. I love this, plus or minus 1 here. Is the Smoot a good unit of measurement? No, right? You have to worry about, is he going to get smaller as time goes by? If I want to figure out something in Smoots, do I have to actually go and physically grab a Smoot myself? This is not a good unit of measurement. We will meet Smoot at the end of the talk. All right. This is the first time I was the head coach. This is Kayla's T-ball team. I am glad to be past that. We're now back into rookies. My son has been on a lot of all-star teams, winning trophies. The goal is to get to the place where you can win trophies. This is wearing a Red Sox World Series championship ring. I will not say because the camera is recording what I offered in exchange to keep it, but I will say I still have my wedding ring and my son. All right. This is a ball we got at Fenway Park. The ball actually, we didn't get to keep it, actually hit a little girl and went backwards, and somebody in the stands got it. And if a little girl is crying because a ball hit her, you have to give her the ball. It's one of the rules of baseball. But my son asked, can I just hold the ball for a moment? So, yeah, this is the closest we've ever gotten to catching a ball. All right, now to the math part. So here are the parameters that I want to use to model a baseball game. RS observed is the average number of runs scored per game. So we just count up how many runs a team has scored, divide by number of games. RA is the average number of runs allowed, and gamma is some parameter constant for sport. There are other sports like football, basketball, hockey, soccer, but these are not great sports. Why is baseball such a better sport than all these other things? Yes?
Does baseball involve a lot more statistics?
Well, I mean, they have statistics in the other sports as well.
But I think that, I just feel like in general the numbers are a lot more valued.
Well, but this could be a function of just who the players are and who the fans are.
Because there's just a lot more data.
There's a lot more data. There's 162 baseball games in a season. There's on the order of 80 basketball, hockey games, and there's on the order of 16 football games. So you have a lot more data. The other thing is you have a lot more individual data. In football, it doesn't matter how great a quarterback you are. If you have no offensive line, you're going to be a stargazer. You know, oh, look at those stars, because you've been sacked again. The Buffalo Bills actually drafted a quarterback who had terrible college numbers because he was on a team that had no offensive line. And what they did is they looked at the statistics and said, you know, on those plays when he had protection, he actually did a good job. But if you don't have a good receiving crew, if you don't have a good rushing game, if you don't have a good defense, you start backed up. It's very hard to isolate how good is somebody in football because you have so many parts that are moving together. Baseball, you can really isolate what is the individual. It's the pitcher-batter matchup. How good are you at fielding? Any New York Yankee fans here? Okay, who's the most overrated defensive shortstop in the history of baseball? Jeter. Absolutely. Derek Jeter is overrated. Now, Derek Jeter has all these phenomenal diving catches and whatnot. The reason he's overrated is a better shortstop would be a little bit faster and would be able to get there in time to make the play. Whereas Jeter's a little bit slower, and so he has all these diving plays and whatnot. But as a fan, what do you remember? You don't remember what looks like a routine play. You remember the great dive. And so the eye can be extremely misleading in terms of what's the right statistic. So one of the things people look at is how many balls were hit to your part of the field and how many of them did you convert to outs. And it's trying to take the human out of the equation because we can be misled by what we see. And so you really want to try to reduce things to mathematics as much as possible. Now you have to take into account for a lot of these things personalities as well. If you don't have people believing the math, when the strategy says this is what you should do, if they're not mentally on board with this, it's not going to work. And so there's a lot of things we know should be done better in football, baseball, and other sports. When the camera's not rolling on Wednesday, I'll tell you about some things I've just recently found out about soccer and a major franchise there. But the players and the coaches don't buy in. And if they don't buy into the philosophy, it's not going to work. So what Bill James numerically observed is a really good predictor of a team's win-loss percentage, which is number of wins divided by number of games, is this average runs scored to the gamer over runs scored to the gamer plus runs allowed to the gamer. And he was doing this with just paper and a calculator back in the 60s and 70s. And gamma was originally taken to be 2. The best fit value of gamma now is about 1.82. So why is this called the Pythagorean one-loss formula? So when James originally did it, gamma was 2. So why do you think it's being called Pythagoras? So we'd have run scored squared over run scored squared plus runs allowed squared. What do you think the connection is with the word Pythagoras?
Well, all the terms of Pythagorean theorem are squared.
Squared, and you have an a squared plus b squared.
Yeah.
And so that's the reason why this is called the Pythagorean one-loss formula. There's a sum of squares. Hey, you need a name. It's a nice, cool name. It turns out this is a really good formula in that it's usually accurate to about 4 games a season. It's very easy to use. Now, in the 21st century, easy to use is not as important as it was back in the 60s and 70s. We have a lot of computational power available. We can have complicated statistics that computers are crunching for us. So this is not as important. One thing that's also nice about this is you can see how it depends on the parameters very easily. We're not doing simulations. We're not doing Monte Carlo experiments. If I increase my runs scored by 10, or if I increase my runs or decrease my runs allowed by 10, I can see which has a greater impact depending on where I am. If I want to value a player correctly, I can see how does their addition or departure affect my predicted win-loss percentage. That's what's really nice about this formula, is you can quickly make these assessments. So just as an example, in 2009, the Sox were 95 and 67. This is how many runs they scored and allowed. The prediction was 93.4. Does that convince you that this is reasonable? Or maybe just as the professor, I'm going to cherry pick something that involves the Sox and looks pretty good. That year, the Yankees were 103 and 59, but predicted to only have 95.2 wins. A lot of times people look at the difference between prediction and performance as an assignment of how well the manager is doing. Is the manager able to use the players a little bit more optimally, put them in a little bit better situations, as to try to determine what is the value added by your manager? Okay, so here are 3 applications. The first is extrapolation. What you can do is you can look at how you're doing partway through the season and see where you are versus where you think you are. So a couple of years ago, the Yankees started off 21-29. It was not a good season for the Yankees. And they have to decide, do we think we have a chance of making the playoffs, or do we think that this season is a lost cause and we should conserve our money and our prospects for the future? Well, all the metrics said the Yankees were much better than their record indicated. And so the Yankees actually spent a good amount of money to bring in a star pitcher and made the playoffs. They were not as bad. Another is evaluation, as I mentioned a moment ago, to try to evaluate a manager. Another is, as I said, advantage that it's a very easy statistic to look at to try to get a sense of what happens when you add players. If you don't care about baseball, substitute the word mutual fund or stock or investment opportunity. You have something and you're trying to find a good way to evaluate it. Now, if you're spending millions or billions of dollars, you don't mind if it's a complicated formula. You don't mind if the computer has to run and chug a little bit. It is nice to have something that's simple and easy to explain. Okay, so basic probability. And one of the reasons why I wanted to do this lecture today is the theme for the next week or so in this course is on integration. One of the biggest applications of integration is to probability. And so if you have some kind of distribution like this, the goal is to come up with some function that models, say, an observed scoring distribution. And then the area under the curve from A to B is the probability your value is between A and B. So if you've taken integration and your teachers have never said probability, they should be prosecuted. I will find a jury that will convict them. It's not a problem. It's why do we care about areas under curves? Only once in my life has someone come up to me and asked me for an area under a curve. And this was in Berkeley, and you got to expect stuff like that there. Why should I care? Why do we spend 2 or 3 classes calculating integrals? One of the big reasons is because integrals tell us the probability that something happens. And that's why we care so much about this. So we will be using this is a motivation to what we're going to do later in this week when we start looking at these integrals. Why do we care about evaluating these integrals? These integrals help us deal with probability. So for probability distribution, it should be non-negative. It should integrate to 1. And then, as I said, the probability between A and B is just the area under the curve from A to B. So the mean or the average value is the integral of x times your density. The variance is a measure of how spread out it is, x minus the mean squared times the density. If all the mass was essentially at the mean, then this would be 0. And the more spread out you are, the larger the variance. The variance would actually have units, say, meters squared if the mean has units of meters. And so what you would want to do is you would want to divide, you would want to take like the square root of this quantity. All right, and then the last concept we need is independence. Knowledge of one random variable gives us no knowledge of the other. And if we're in a situation like that, we say the 2 variables are independent. So whether or not I choose to give the lecture today and how the Red Sox do today are probably independent events. If they are not, please let me know immediately and let me know what I should be doing to help the hometown team. Okay. How many of you have ever seen the old Charlie Brown baseball cartoons? One person has seen them. Things never go well for Charlie Brown's team. And so here are the 2 guidelines for modeling. The model should capture the key features of the system, and the model should be mathematically tractable. And the reason I have the picture of Charlie Brown here is these are mutually contradictory statements. They pull you in different directions. The more features of the system you capture, the harder it's going to be to model. And the more you can model, the more tractable your system is, the less you're capturing. So you have to decide what captures enough to still be useful. And sometimes you may no longer be able to get a closed form solution. You may need to get something where you have to do simulations. For the voting procedure problem, this is a problem-solving class. This is your chance to actually influence the voting policy of a national organization. We've got to convince people to vote for our policy. We've got to convince them that it's fair, that it's going to lead to resolutions in a reasonable amount of time. We're not going to have this 6-ballot crap again. And so we'll do some simulations. We'll come up with maybe different voting profiles. If you're interested in voting theory, there's a beautiful theorem called Arrow's theorem, which basically says if you have a couple of principles about voting to have voting fair, you can't have all of them hold. So I'm not going to go into too much detail right now. If we're interested in that, that's definitely something we can explore. There are trade-offs. And this is one of the biggest things to learn. When you take a theoretical class, we have these nice, beautiful, crisp, statements of theorems, and then we have the proofs. When you get into the real world, things are messier. And you have to decide, what must you have, what can you live without? I will try another movie reference. How many of you have seen Spaceballs? All right. What am I thinking of? Things that you might just have to live without. The industrial strength hairdryer. All right, so if you remember that scene in Spaceballs, that's something you can live without. You'll leave it in the desert when your life is being threatened. All right, so here's a possible model for baseball games. Runs scored and runs allowed are independent random variables, and they're given by some density function. Yes?
Is it true that they're independent though?
Well, that's my first question to you. So this is when I look at my watch and see how many minutes are left in the class, and then that's how much time I give you to pick apart this model. So why might they not be independent?
Because if your team is I think it's related that if your team is bad enough to allow a lot of runs, then perhaps their offense might be relatively bad in the sense that you score less runs than average.
Or if you're in a game and you're up by 20 runs, you might throw in.
Right.
Oh yeah.
Yeah. So if you have, so as was just said from the class, in case you can't hear this at home, if you have a huge lead, you might pull some of your better plays and give them some rest, or you might put in weaker plays and give them a chance. Years ago, the Sox had a pitcher they picked up named Rumlinger, and when he came in, one of the statistics you often give a pitcher when they enter is the ERA. But Fox Sports didn't give his ERA; they gave 3 dashes. And the reason they gave 3 dashes is ERA is runs allowed divided by innings pitched. Oh, well, actually divided by, it's per 9 innings pitched. He had yet to get anybody out as a Red Sox. He'd allowed runs, he just hadn't gotten anybody out yet. So as a division by 0, his ERA was plus infinity. And they just didn't have the symbol for plus infinity. Now the Sox were up 10-3 in the 9th inning. 7-1 lead, sure, let's have Rumlinger, let's see what he can do. Very quickly he gave up a grand slam. Bases loaded home run. He did get 3 outs before the inning ended, and he got the save. He actually created a safe situation. So he would never have seen the field. Okay? So this is one way in which the runs scored and allowed might not be independent. Also, if you're losing by a lot, you might give up on the game as well, and you might put in other people. Here's an interesting thing. Anybody remember the former Commissioner Bud Selig? He instituted a rule to prevent a catastrophe from happening. We don't have time to describe in detail why this would be such a horror for humanity for this to happen. But Bud Selig has made sure we will never see this again in a baseball game. Anybody know what this is? Baseball games cannot end in a tie. Other sports can survive a tie, but baseball, it would be catastrophic if a game ended in a tie, and Bud Selig has declared that this will never happen. So years ago, the Sox and the Orioles, again the Orioles, they were playing on Mother's Day, and the game is called the Mother's Day Miracle. The Red Sox gave up 5 runs to the Baltimore Orioles. What can you tell me about how many runs the Sox scored? What can you tell me? Not 5. Runs scored and runs allowed can't be the same, so if the Orioles scored 5, the Sox did not score 5. Going into the bottom of the 9th, the Sox had 0 runs. They scored 6 runs in the bottom of the 9th, with the last 1 or 2 coming from an error on an easy throw. And this is why the game is called the Mother's Day Miracle. But we know that these numbers can't be the same. This leads to some great statistics. It's similar in some of the statistical analysis you'll get when you're looking at what happens when you go in a doctor's office or hospital. Hopefully when you go to a hospital, you don't leave sicker than when you arrived. Now occasionally it's sad they remove the wrong organ or amputate the wrong leg. This does happen. And then you've lost that and you still have the original ailment. But when you're trying to analyze what happens, you often make the assumption we're not going to get worse. And then when you're looking at what opportunities are accessible, that affects things. This affects the statistical analysis. How many of you have taken a stats class? Okay, so this is RBC contingency tables and how you handle when not all the cells are accessible. This is actually what got me a call from one of the senior quant people at an MLB team, is I actually handled issues like this in my paper, and he wanted to know how this was done. So to calculate the probability a team wins, we have two possibilities. We could model things discretely, or we could model things continuously. So in the discrete case, what I assume is I allow j runs, I score I runs, j is less than I. Or I allow y runs, and because the probability that x equals y is 0, because if it's an integral, I then score x runs where x is greater than or equal to y. For a baseball game, which do you think is better, continuous or discrete? Discrete, right? The Sox are never going to beat the Yankees by a score of pi to e. I'd love to see that, in the box score, right? A transcendental game happened last night as the Sox triumphed, though we don't know if the difference is algebraic or not. That's not going to happen. However, I'm going to choose to model baseball with integrals and continuous probability distributions. Why would I choose to do that when baseball scores are discrete? How many calculus classes have you taken? 3, okay? You should all have taken 3 calculus classes by now, okay? How many advanced summation courses have you taken? None, right? Hammer time, right? What do we know how to do? We know how to integrate. We have a lot of integrals we can do nicely. Why are we going to do things with integrals and continuity? Well, that's what our skill set is. And again, this is far more important than anything else I can teach you. Know what you're good at and find a way to use it. So we've talked about some of the problems. One is, what are the explicit formulas for the densities? Are they independent? They're not. And can we actually compute the sum in closed form? So what would you assume is the easiest choice we could take for our densities? Simplest choice, to make the integrals as nice as possible. So uniform, right? Uniform is the simplest thing we can do. This is going to be really easy to do the integrals. The problem is the uniform distribution just doesn't describe real-world data. Anybody have a thought as to what the next choice might be? Okay, normal is next. Good, excellent. So there is a problem. There's 2 problems with the normal. One is, there is technically a possibility you could score 15 quadrillion runs. Now, the probability is smaller than being hit by 15 consecutive meteors while winning the lottery, but it's possible. But it's such a small probability, we don't really worry about it. And it's often easier to integrate from minus infinity to infinity and just not worry, because we're going to assign such a small probability, not a big deal. There's another problem with the normal, and that is the fact that we have a probability of scoring a negative number of runs. No matter how bad your team is, you will not score a negative number of runs. I have toyed with giving exams where you start off with 50% credit on each problem, and you can go up or down depending on whether or not you write things that are correct or incorrect, and actually give points for knowing when you don't know. I somehow feel that that would lead to a suboptimal response from students, so I have not done that. But it would be interesting to see how that would affect how you choose to do tests. When would you decide, I think this is right, but I'd rather just play it safe and take the points here because I'm more comfortable on some of these other problems and I think I've got enough points. Next thing you could try is an exponential. This has no negative probabilities, for negative runs. It does go off to infinity, but it goes off to infinity so slowly that it's not bad. The problem is it just doesn't describe the data well. So what I want to introduce you to is the 3-parameter Weibull distribution. And again, this goes back to the more tools you have, the more things you can do. So the first thing to notice is all beta does is it just shifts my whole distribution. So if you're playing basketball at the pros, it's hard to score fewer than 40 points. So you wouldn't want your probability distributions to be starting at 0, you would be starting at 40. The next thing is alpha, it changes the scale. Think of it as converting from centimeters to inches to smoots. Not a big deal. The one that really matters is the gamma. That fundamentally changes the shape. And so, here's a couple of different values. If you take gamma as 1, you get an exponential. And then, here's some other choices. For the most part, these are technically called one bump or one hump distributions. You go up, you go down. It turns out these model a lot of things. And so they arise often in survival analysis. If gamma is less than 1, this is a high infant mortality. You don't get to live to old age. Gamma greater than 1, an aging process. It would be interesting to look at, age or years at Williams of faculty members. Do you think there's a high mortality, or do you think most people make it through? Now, it turns out we can calculate things like the mean and the variance very easily. So there's a beautiful function called the gamma function. Have we talked about gamma in this class? It generalizes the factorial function. We'll talk about it on Wednesday. It's defined as e to the minus u to the s minus 1 du, or you can write it in the second way with the du over u. The reason this is nice is if I change my scale, if I change u by a factor of 5, the du over u is invariant. Now, I will get a change from the u to the s. But it turns out this is a really good way to think about it. I'm looking at a multiplicative measure on the positive real line, rather than a translation measure, which is what we typically do with the dx. By integrating it by parts, it turns out gamma of n is n minus 1 factorial if n is an integer. Gamma of 1/2 is the same then as negative 1/2 factorial, which is the square root of pi, which is an extremely important number. You can calculate the mean and the variance of the Weibel distribution in terms of its parameters, and they're really nice answers. So I'm not going to go through the integration slowly. The slides are online. What you basically do is you notice, ooh, I've got crap to the gamma minus 1. This is screaming at me, change variables, let u equal crap to the gamma. Du is crap to the gamma minus 1. Everything comes out nicely, and now I'm just integrating an exponential with a u. Oh, play little games, and it's a gamma function. So this is one of the reasons I like the Weibel, is I can get closed form answers in terms of the parameters. And because I have 3 parameters, I can actually get a lot of different shapes. I had a thesis student who worked with me on linear combinations of Weibels, which gives us even more freedom in terms of what we can do. But it turns out it doesn't really do much better job in terms of modeling what happens. That even though it's more flexible, the Weibel is already close enough to what's going on that there's really no need to make the model more complicated. The reason I actually thought to do this is the special case when gamma equals 1 is the exponential, and I know how to do that. The case when gamma equals 2 is a distribution you see in various problems in physics and random matrix theory. So I was actually just playing with distributions I knew. And when I saw the answer for the exponential and the answer for the gamma equals 2, I go, oh, wait a minute. If I just put in this parameter here, and then I did some such, oh, it's called a Weibel distribution. Oh, wonderful. But it's what do you know? And so I got this because of some random matrix theory I knew. And this is something most people looking at the subject haven't seen before. And it got me thinking about it in a different way. So on any web page, this is from either MLB or ESPN, I think it's MLB, space on a web page is precious. You often have to make sure you have enough space devoted to advertisements, right? They bring in money to the website. So when you look at the stuff that's being displayed, they've got to choose very carefully what they want to explain. Okay, you really need the team name. That's got to be there. The wins, losses. You don't really need the winning percentage because you can get that implicitly from these, but most people are not going to do the calculation. You want to have that there. It tells you how many games back a team is, how they've done in the last 10, what their streak is. INT is interleague play, how they're doing against the other league. Home record, road record. And then XWL is the expected win loss. So this is how important the statistic is. This is one of the few things they choose to display. And you can see how this compares. So, it's of course a coincidence I chose the date the Sox went first. The Sox were 37-25, predicted to be 36-26, 27-31, 28-30. It's not doing a bad job. So I'm going to skip this now. So don't read these next few slides, but this is a nice problem that I might give you. Okay, so here is the Pythagorean one-loss formula. So I proved this when I was a postdoc at Brown. So imagine runs scored and runs allowed are independent random variables drawn from Weibels. Assume they have the same beta, the same gamma, but they can have different parameters for runs scored and runs allowed. Then the probability that a team wins is the following, which is essentially the Pythagorean prediction. beta is always going to be a half. Or, yeah, it's always going to be a half. And the reason is baseball scores are integers, 0, 1, 2, 3. I don't want to have my bin 0 to 1 open interval, closed interval 1 to 2 open interval. Because if I score 1 run, I'm in the second bin, but I just barely missed the first bin. I want my discrete scores to be the centers of the bins. So the first bin goes from minus a half to a half. The next is from a half to 1. I'm sorry, to 1.5. And now your scores are right in the middle. They're well separated. So that's why beta is negative a half. And then it turns out that you can estimate the run scored minus beta in terms of the gamma parameter, the gamma function, and the Weibull parameters. And so if you know how many runs a team scores, you can then work backwards and figure out what the parameters are. Or if you know the parameters, you can figure out what things are. So we need to calculate the probability that x is greater than y. So this is now integration. But this is integration that matters. So I have to do this double integral. And there's a beautiful technique here. So again, the purpose of problem solving is to teach you how to reduce things to things you've already seen. Okay? How many of you have seen physics? Right. So I'll be curious to see if you can recognize the physics that comes into play. So the first is, rather than integrating from beta, just change variables, so I go from 0. So now I have this integral to do. Well, I do my change of variables as before. And now I get a really nice thing from I get an exponential and I evaluate at the two endpoints. Well, since this is a probability distribution, when I hit it against 1 and I integrate, the integral of a probability distribution is just 1. So I'm left with the following. This almost looks like a Weibull. The problem is that the exponent I have over here is not the same as what I have down here. I have a x over alpha RA, I have an x over alpha RS to the gamma, so I can combine them like this and come up with a new parameter alpha. Well, then all I'll have to do is just play games here and just multiply by appropriate powers of alpha, and it'll be a probability distribution, and I can do the integration. So does anybody recognize this from physics? It occurs in two places in physics you might have seen. In center of mass calculations, when you have two masses, and in resistance, when you have two resistors. I always forget if it's in series or parallel. I think it's in parallel. If not, it's in series. But what's the net effect of two resistors? I think it's parallel, because if it's in series, I think you just add the resistance.
Yeah,
it's parallel. So, this is a trick you should have seen in some physics classes. This idea of coming up with a new parameter in terms of the other ones and interpreting this as a new problem. And now the integration is just a bunch of algebra. You end up getting the following. You then expand things out, and voila. So now we want to analyze the season. So here's some data from 2004, a completely random season. Here's runs scored, runs allowed. Looks pretty good. And then what you want to do is, if you've taken statistics, you have what's called method of least squares or maximum likelihood. You look at your prediction minus the observed, square it so that errors cannot cancel. And you want to choose the value of your parameters that gives you the smallest value. And so that way you can do things better than, it looks like a good fit. So when you're looking at what's going on, it doesn't look like it's doing that bad of a job. Pretty good fit. No, I'm a little concerned over there. Wow, look at that wonderful decay. So really, the only issue among these ones over here was this didn't look so great over there, and then the last one looks a bit off. But this is the Toronto Blue Jays, they're Canadian, so maybe it's a metric hit? No. Has absolutely nothing to do with it, they're Canadian. It turns out if the data is too good, you should be suspicious. And so, imagine we flip a fair coin 1,000,000 times, you expect 500,000 heads. 95% of the time you'll be between 499,000 and 501,000. If you do 1,000,000 flips n times, you can ask what's the probability that at least one set is outside that range. If you have 14 instances, you have a 50% chance that at least one is outside that range. There's 14 teams, or there were 14 teams in the American League back when this happened. Or maybe it was the National League. And so you expect at least one team to be a little bit off. And so when you look at the analysis, there's something called a chi-squared statistic. I'm not going to get into all the advanced statistical stuff over here, but when you look at the Toronto Blue Jays, they were a little bit off what they should have been. It was 14.18. It should have been 14.14. There's something called the Bonferroni adjustment. So if you've taken statistics, it allows you to take into account the fact that you're doing multiple comparisons. And when you do this, it comes out to be really good. And it really is doing a great job. So I've mentioned over here the structural zeros. I'm not going to go into that now because this is not a statistics class. But if you're interested, let me know. There's some great stuff to read here about how do you handle comparisons when you have certain things that are not accessible. All right, so in summary, it does a pretty good job. The best value I get for the mean is about 1.74, standard deviation 0.06, median 1.76 for the exponent gamma. And just trying to find the best fit value gamma when you look at the data is about 1.82. So it's doing a really good job very easily. It's giving you some reason to trust this. You know, this is the old David Hume from philosophy. Just because the sun has risen every day in your life is no reason to be sure that it will rise tomorrow. I'd still bet on it rising tomorrow, but it's not a proof. This gives you some reason to trust why this might be happening. There's a lot of different stuff you can do. There's a lot of things you can take into account. I'm not going to go into all this microanalysis, but there are ballpark effects. Different ballparks are hitter friendly or pitching friendly. You may want to adjust the runs scored and runs allowed to take into account the environment they were created in. You can definitely do that, and then the math theory would still be the same. The last is to seize opportunities, never know where they will lead. So this is, Smoot's years after he was an undergraduate at MIT. Anybody know whatever happened to Smoot's? I love this. Chairman of the American National Standards Institute. President of the International Organization for Standardization. Well, my qualifications, I am a unit of measurement. So, to me, it's always fascinating as to where life will take you. So many of the times, I've had small little things that have happened to me and I've seized the opportunities. As a mathematician, this is one of the greatest advantages you have. You are problem solvers. I've written papers in accounting, in marketing, in computer science, in economics, in statistics, in physics, in geology. Talk to people. You have a different skill set than they do. You can often pick up enough of what they're doing to be useful and say, okay, this reminds me of some mathematics I've seen. If you do physics, electricity and magnetism and gravity are very similar for a lot of things because you have a 1 over r squared force for a lot of things. And solutions in one area can often translate to another. This is one of the biggest themes, and this is one of the reasons why I thought the batteries died. This will be interesting to see how much of it recorded. And these are the same people who say Pythagoras. This is something that a lot of people have complained on over the years, that grammatically is incorrect. You are absolutely correct.
Thank you.
Yep, have a good one.
Thank you.
Have a good one. Good morning. How's it going?
Good. Excuse me, are you Professor Miller?
Yes.
Hi, I'm Oliver. I'm a visiting high school
Oh.
student. Is there room in this class?
There is. It's a shame you weren't here an hour earlier.
Was it the same class?
No, it's not the same class, but I was doing a lecture on integration and baseball mathematics.
Oh, okay.
And so that class had absolutely no prerequisites.
I'm from Chicago, so, you know, the Cubs.
Well, I was going to say, so are you White Sox or you Cubs?
Definitely Cubs. I live on the north side.
Oh, you live on the north side. Okay.